So, welcome to this third lecture. So, in the previous lecture, we saw some of these topics. So, first one, we saw how to measure the information content. So, information content is measured by this equation, that is I of mi is equal to log of 1 by p. And then we saw how to measure the average information content or the entropy of the message. So entropy is given by the equation h of n is equal to pi log 1 by pi for all the messages emitted by the source. And later on we saw how to measure the information rate. So information rate is entropy multiplied by the rate at which the source emits information per second. So altogether we saw all these parameters for an independent source. In today's lecture, we will see how to measure the entropy or the information rate for a dependent source. In the previous lecture, we also saw what's the difference between an independent source and a dependent source. So today's lecture will mainly target the dependent source, or also called as a Markov source. So the first concept is average information content of a dependent sequence. So a dependent source, here the symbol emitted depends on the occurrence of the previous symbol as well. That means current symbol will be influenced by the previous symbol. So this is called as a memory source. It remembers what was the previous symbol. Accordingly, it is going to generate the current symbol. That means its probability of occurrence will be decided by the previous symbol. So it's called as a memory source, or it's also called as a Markov or Markov source. So one of the examples is mentioned here, that is English language. So in case of English language, we know some letters or some words will have more frequency. For example, there are many words starting with S. Similarly, some of the words will have Q and U. They occur together. So that means there is U and there is Q. That means if Q appears, then U appears. For example, in case of queen or quick or quench, these are some of the examples. That means they should occur together. So they are dependent on one another. So here we call such dependent sources as Markov sources or Markov, maybe Markov or Markov sources. Or this process is called as Markov process because it's basically a random process, and the probability of occurrence, that is dependent, depends on the previous event or previous message or information. So we will see how to measure the information content or the entropy if it's a dependent source. So here, as mentioned, the two versions of mentioning is either Markov or Markov. So we represent the probabilities and state of each source. If there are multiple sources, we can represent it graphically. We will see that here. So that's also called as a state diagram. So I think when I give the example here, it will be more clear. So we'll assume that there is a source that emits different symbols like A, B, and C. As shown here, okay, here, a source emits different symbols A, B, and C are shown here. So, and also there are some arrow marks and some values on the arrow mark, right, beside the arrow. What's the meaning here? For example, A is one of the states, and then there is an arrow indicating back to A, right? So it indicates that currently, if the source has emitted a symbol A, then the next symbol would be A with the probability of 0.3. And in case if A has the current symbol is A, then the next symbol would be B with a probability of 0.7. Similarly, the concept applies to all these states. So these are called as transition probabilities. That means from one state, it wants to go to the next state, then what is the probability transiting from one state to another state? And the value here that indicates the probability of such a transition. So in the next slide, we see, okay, yes, here. So in this slide, we have shown in more detail. For example, this is the same figure, but more clearly. So P of xk plus 1 is equal to A, xk is equal to A. So you may know what are these? What is the representation here? This is called as a conditional probability. In a dependent source, we use this term, that is conditional probability. That is xk. What is xk? Xk is the state of the source. So if the state of the source is A right now, that is kth state is A, then what would be the k plus 1 state? The probability of k plus 1 state, that's equal to A. So what's the probability of this? That is equal to 0.3. The meaning is currently the source emits A, and that is x of k is equal to A. And what is the next state? The k plus 1 state. The k plus 1 state is also A, and its probability is 0.3. Okay, that's a transition probability. And if the current state x of k is equal to A, and the next state x of k plus 1 is equal to B, where is that here? So current state is A. From A, it can transit to the next state, k plus 1, that is state is B. Then what's the probability of such a transition? Probability of transiting to x of k plus 1 is equal to B, provided the current state is A, that's equal to 0.7 as shown here. So current state, that is x of k, what is that? That is A. What is the next state? X of k plus 1, that is B. So what's the transition probability? So that's a whole thing here. That's equal to 0.7. That's what mentioned here, 0.7. This is a transition probability from the current state to the next state. Okay, from the current state A to the next state C, what's the transition probability? That is mentioned here. Current state is A, the next state is C, and such a transition probability is equal to 0. That is right, because from A, there is no arrow going to C. There is no outward arrow going to C, right? That's why this source will never emit A and C. It may emit A and A, or it may emit A and B, but it never emits A and C. So such a probability, such an event never occurs, so its probability here mentioned as 0. Okay, now we'll also see if the current state, that is x of k plus 1, after the transition is B, then what would be the state x of k plus 2? In the previous slide, we saw the transition from x of k to x of k plus 1. In this slide, we will see the transition from x of k plus 1 to x of k plus 2. Okay, we will assume that x of k plus 1 is equal to b. That means right now we are seeing, or we are assuming that the source has emitted b. Then from b, what are the different possibilities in the next instant of time, x of k plus 2? So from if x of k plus 1 is b, it could be anything, but right now we are concentrating on b. If x of k plus 1 is equal to b, then what is x of k plus 2? It could be A or B or C. And what's the probability? We'll see that here. So here if x of k plus 2 is equal to a, that is from B you're moving to A. There is no such transition defined here. That's why its probability is 0. And then from the state of B, x of k plus 1, the next state is x of k plus 2 is equal to B. What's the probability of such an event? From B back to B, there is no such transition defined here. So its probability is also 0. Okay, now here, current state is B and next state is C. What's the probability? From B to C, yes, the probability is 1. That means it's very definite. From B to C, there is always transition. I mean, in this example, the source emits, if the source emits B, then it will definitely emit the next symbol as C, and nothing like B and A, B and B, that never exists in this case. So if such a state diagram is mentioned, you should be able to write the conditional probability. In case if the conditional probability is given, then you must be able to write its state diagram to analyze further. So this is one of the tasks or one of the skill you need to acquire from this discussion. Okay, let us move on. We will see another little more complicated example here. So this is again a Markov source, dependent source that emits three alphabets like A, B, and C. Here again, as we said, it's a dependent source. A probability of occurrence of any symbol depends on its immediate previous symbol and not on the entire past history. For example, if we have AB as a symbol or a message generated, then B will depend on A, only the previous one. For example, if there is ABC, the C will depend on B, but not on A. That means only the previous one on which a current symbol, the current message depends on. Okay, we have a detailed diagram here. So from the previous discussion, you must be able to understand what's the meaning of this state diagram. So there are three different states mentioned here. So this circle indicates a state. For example, currently the source is in state 1, or it is in state 2, or it's in state 3. We will analyze one by one. If currently the system or the source is in state 1 and it emits A or B or C, then what would happen? In case we assume that it's in state 1 and it emits A, then the next symbol or the message it emits A with the probability of 1 by 2. Or from the state 1, it would emit C with probability of 1 by 4 and reach the state 2. Or from the state 1, it would emit B with the probability of 1 by 4 and it would reach the state 3. Similarly, the concept applies to every state. Okay, the more details here. So in this figure, the same figure, the source emits A first. If this just we are assuming it can emit A or B or C. Right now we'll start from any one. Okay, so if the source emits A first, then it is emitting A first, means it's in state 1. Then next it emits A with the probability of half. So there is an arrow back to A here, right? So it indicates that it's transiting from state 1 back to state 1. In that case, it will emit the symbol 1 by 2. So states are nothing but different stages when it emits the messages. Okay, so if it does so, then it will come back to state 1. Or from state 1, it emits C with probability 1 by 4 and goes to state 2. This is what I mentioned in the previous slide. That is, from the state 1, it emits C. You can see here, this is an outgoing arrow from 1, and the symbol generated will be C, and the next state will be 2. Similarly, you see here the outgoing arrows from state 1. Where is the outgoing arrow? Here, right? So this is the symbol emitted B with the probability of 1 by 4. And if it emits B, then it would be reaching the third state. So this is basically state diagram. We are just representing these as transitions by different states. If it emits this symbol, particular symbol, then what next? We name it by different states. Okay, that is what mentioned here. It goes to state 3 by emitting the message or symbol B with probability of 1 by 4. Similarly, from state 2, initially, if it was initially in state 2 where it emitted C, it can come back to C with the probability of 1 by 2, or it can come back to state 1 by emitting symbol A with the probability of 1 by 4, or from the state 2 it will emit B with the probability of 1 by 4 and reaches state 3. Similarly, for state 3 you can analyze by yourself. So we have also considered here that initially the source may emit one, I mean, the symbol A or symbol B or symbol C with equal probabilities. So initially we do not know the very first symbol what would be. It would be A or B or C. Okay, but later on we can define based on this diagram or conditional probabilities. In case if I had emitted A first, then there is 0.5 probability that it will emit A again, and there is 0.25 probability that it will emit C, and also there is remaining 0.25 probability that it will emit B, and so on. But initially, which one? Maybe A or B or C, they are equiprobable. That's probability is 1 by 3. Anyone can occur. Okay, based on this state diagram has given us some information like moving from one state to the next state. But tree diagram will give us an idea if the source has emitted many symbols, because we are dealing with a long sequence, right? So if there are many symbols, then how to find out the transition probability? That is what we get with the help of a tree diagram. So in the case of tree diagram, we will be seeing three symbols, four symbols, and so on. If it is just two symbols, then we can easily do that with the help of a state diagram. That means currently I am in state 1, I want to go to state 2. Then uh, the previous state diagram is sufficient. But a tree diagram will give us an idea to find out the total probabilities, transition probabilities, if there are three symbols generated, 4, 5, and so on. Big number of, if it is a long sequence, then tree diagram is much convenient. Okay, the tree diagram is will appear something like this for the previous transition diagram. We will see how this can be generated. You need to write it by yourself. How to write this kind of a tree diagram if the state diagram is known. Okay, so in the previous state diagram we saw initially the source emitted as A, and it was in state 1 with the probability. We said initially it can be in any of the states. So we assumed that if it was in state 1, its probability was 1 by 3. This is what the information given to us. That is what written. No? Okay, we will start our uh, process of writing the tree diagram from here. So initially we assume that the source emits symbol A and it's in state 1. Next, what happens next? What are the different possibilities from state 1? From state 1, it will emit symbol A with the probability of 1 by 2 and goes to the next state. That's also 1. Or from the state 1, it emits C with the probability of 1 by 4 and reaches state 2. Or from the state 1, it emits symbol B with the probability of 1 by 4 and it reaches state 3. Is it so? So just to see this part of the figure, only this. From 1, how we can reach 1, or from 1, how can we reach 2, and from 1, how can we reach 3? What are the symbols A, C, and B, right? So this comes from the previous figure here, the state diagrams. From 1, it can go to 1 by emitting symbol A. From 1, it can go to 2 by emitting symbol C with this probability. From 1, it can go to 3 by emitting B. So from 1, it can go to 1, 2, or 3. Then the emitted symbols will be A, C, B, right? So this is what's shown here. A, C, B. It is going to 1, 2, or 3. Okay, yes. This is the fundamental step, and then we will use this same step afterwards. That is, in the next stage, why do we need to build so many stages? I will tell you. Okay, in the next stage, what's going to happen? From state 1, because there are only 3 states. So from state 1, if it emits A, it will go to state 1 again. From 1, it emits C, then it will go to state 2. From 1, if it emits B, then it goes to state 3. That is what mentioned here, right? From state 1, what are the different possibilities? It can go to state 1 again, state 2 again, or state 3. And these are the symbols that are emitted, A, C, and B, as shown here, A, C, and B. So basically, this is the repetition of this. Okay. In case we will see the next part. We will see the next part. Suppose the initial state was 1 and now it has arrived here to the state 2. From state 2, what are the different possibilities? From state 2, again, it may go to state 1, or it may go to state 2, or it may go to state 3. Then what happens? Can we refer back to the previous diagram? Yes, here. From state 2, it can go to state 1, or it can come back to state 2, or it can go to state 3 here. Okay, so what are the symbols generated? A, C, and B. A, C, and B. From state 2, A, C, and B, then it will be transiting to the next states of 1, 2, and 3, right? This is what we have seen. Okay, now we will continue further. Initial state was 1, and we saw how to arrive at state 3. And then from state 3, what are the different possibilities based on the previous state diagram? From state 3 also it can go to 1 or 2 or 3. And what are the different symbols generated? Let us see that from the previous state diagram. From state 3, it can uh, go to 2 with the generating symbol C. It can go back to state 3 by emitting symbol B, uh, or it can go to state 1 by emitting symbol A. That is what we are going to write: A, C, and B. That is 1, 2, 3. A, C, and B. If it emits, then accordingly it will be transiting to state 1, 2, or 3. So this is the case if the initial state was 1 or the symbol generated was A. So what it says? So it says initially the source emitted symbol A with the probability of 1 by 2, and then it again emitted A, and then it again emitted A, and total symbol generated will be A and A. Or initially its state was 1, and now it emitted A, and then it emitted C. So the total symbols generated by the source is AC. Okay, from the initial state, it generated A and then it generated B. So the total message generated is AB. Or from the initial state 1, it next one it generated C and then it generated A. So the total symbol generated is CA. So these are the two messages generated after the first state. After the first state, it is going to generate C and A. So if you say another stage, maybe the source emitted three symbols, then we need to build this tree to one more level. That is one. It will have one more transmission. One, two, three. From two also one, two, three, three, one, two, three, and so on. The same process continues here, and you need to copy the values from here to the next stage. So then we will be having three symbols generated. For example, A, and one more A here in the next branch of the tree, and so on. So that gives three symbols generation, four symbol generation. You need to find out the total probability in that cases also. Okay, this is for the first state. Similarly, for the second state, if the initial state was 2 with the probability of 1 by 3, then what are the different possibilities? From state 2, what are the different possibilities? It can have A, C, or B, right? Actually, you can copy from here A, C, or B, or you can refer back to the previous figure. From state 2, what are the different possibilities? Initially, if it was in state 2, then it may emit A or C or B, and then go back to, reach states 1, 2, and 3. Okay, we'll just quickly see the previous state diagram. Okay, here, initially its state was 2. So until now, we discussed about state 1. From state 1, how to go to different states. Now we'll see the second part of the tree. We'll talk about this. From state 2, how to go to state 1 or state 2 or state 3. So to do that, it has to emit A, C, or B, right? So we will see that here, A, C, or B with these probabilities, and it will reach 1, 2, or 3. Again, from this state, from state 1, that means it has transited from state 2 to state 1 and emitted symbol A. Now from state 1, what are the different choices we have? I mean the source has. It can emit again ACB and reach 1, 2, 3. This is what the repetition from here or maybe from here. I mean, basically we're talking about the transition from state 1. State 1 you know already, so this was transitions. Suppose if it was in state 2 and again it came back to state 2, then what are the different choices at state 2? Every state has a defined choices. For example, in state 2 we have A, C, B, right? The same will continue. From state 2 it has only three choices, A, C, B. Similarly, state 3, if it has come from state 2 to state 3, at a state 3 what are the different choices we have? We can refer back to the previous diagram, or already we have done that here. From state 3 we have these three choices. The same will continue even here because it's the same transition diagram or state diagram. Okay, now finally the third state. From state 3, what are the different choices we have? 1, 2, or 3. So it has to emit these three symbols. From 1 it has again three choices. From 2, similarly from 3 it has three different choices, and we know what is the transition probability here. So this altogether, this tree gives us the transition probability of emitting two symbols. For example, from initial state 3, it will emit A and emit A again. So total probability is 1 by 4, 1 by 2. There is a way how to compute that. That we will see in the next slide. So right now you got the idea of writing a tree diagram given its state diagram. Okay, now we will find out how to calculate the entropy. So entropy of the source is the weighted average of the entropy of the symbols emitted in each state. So now entropy of a state I is Hi. So that is given by the equation Hi, that is entropy of a state, maybe state 1, state 2, or state 3. is nothing but Pij log 1 by Pij. This kind of equation we have seen even in case of a independent source. The entropy is Pij, or there it was Pi, here it is Pij log of 1 by Pij. So Pij indicates what? I is the current state, J is the next state, because this is a dependent source. So here probability of transition probability from state I to state J. What is the value? Similarly, log of 1 by Pij. So this has to be calculated for all possible states. A source can go from a particular state I. That means assume that currently it is in state 1. Then what are the different choices? It can go back to state 1 or state 2 or state 3, right? Then what is the conditional probability to do that? That is what we are writing here. That is a summation mentioned here. See, the summation start from j to n. N is the total number of states a source, sorry, from one state you can go to. So currently it is in state 1, I is equal to 1. Then what are the different choices it has got? Maybe it can go to state 1 or state 2, state 3, state 4, and so on, right? So that is the condition probability here. For all those we need to compute. Okay, so how many states we have? There are many states. Maybe from state 2 you need to go to state 1, 2, 3. Similarly, from state 3 you need to go to state 1, 2, 3. All that we need to compute. So that gives the total entropy. So then, so that's what mentioned here. The entropy of the source is the average entropy of each state. So that's given here. The entropy H is equal to I is equal to 1 to n pi hi. What is that? That is basically for every state you have some initial probabilities multiplied by the transition probabilities. So this is what is here, transition probability. That is what is the hi here, multiplied by pi for every state. There's so many bits per symbol. So we have an example, you'll come to know that. So what is here? The new term of pi, capital Pi, is the probability of a source when it is in state 1 or state I. For example, in the previous example, we considered that every the source can be in any of the states. Maybe initially it was in state 1 or 2 or 3 with the probability of 1 by 3, right? So that is what Pi represents. It's a initial probability of a state. Okay, the next concept is information rate. How to find out the information rate? Information rate is nothing but entropy multiplied by the number of state transitions per second. It is similar to the information rate equation in case of an independent source. Okay, then we also have the next term, that is the average information content per symbol. So this is computed by this equation here, Gn. That's equal to summation PMI log 1 by PMI. You know this, you are very familiar with this term. That is computed for all i's or all states. Then also it is averaged here 1 by n. So n is the total number of messages in a long sequence, or total number of symbols as given here. It's the length of the symbol. We will see with the help of an example here all these three concepts. Okay, given a state diagram or transition diagram, how do you find the entropy of every state? How do you find the entropy of the source? And how do you find the average information content Gi? So based on the previous equations we are applying here. Okay, we will start with the first one, entropy of a state. So entropy of a state is given by this equation Hi. You have to just refer to this figure and find out how many states are there. There are three states, 1, 2, and 3, right? So all the three you need to find out. Hi is equal to summation for all the states, transition states, Pij log 1 by Pij. Okay, for state 1, what are the different possibilities we have? From state 1, it can go to state 1 again, or it can go to state 2 through here, or it can go to state 3 here, right? So Pij 1 to 1 and log of 1 by Pij plus for state 2, 1 to 2. What is that? 1 to 2. Pij, that is 1 by 4 log 1 by 1 by 4 plus the third one. From 1 transiting to 3, the Pij is 1 by 4. So 1 by 4 log 1 divided by 1 by 4. So totally you get so many bits per symbol. Now, similarly, you have to find out for state 2 as well as for state 3. Okay, for state 2, what are the different possibilities we have? Either go to state 1, state 2, or state 3, right? So if it's going to state 1, then here the condition probability is 1 by 4. If state the next state is also 2, then probability is 1 by 2. That is what mentioned here. And if it wants to go to state 3, it is 1 by 4, right? From state 2 to state 3, here 1 by 4. So you find out what's the number of bits per symbol. Similarly for state 3, from state 3, it can go back to state 3 or go to state 2 or go to state 1. So that is what mentioned here. Okay, this gives the entropy of every state or any ith state, right? For state 1, state 2, and state 3, this is the entropy. Now we need to find out what's the entropy of this entire source. So that is nothing but the sum of the entropies of every state with the weight or the probability of every state. Okay, in the previous case, we saw how to find out the entropy Hi for every state. For Hi is 1.5, right, in the previous slide. That is a common value for everyone. I mean, based on the equation or based on the values, that comes to be 1.5 in every state in this example. So H1 was 1.5, H2 was also 1.5, H3 is also 1.5 in the previous slide. So that is what we are writing here. So Hi multiplied by Pi. So H1 multiplied by P1. What was the probability of any state? We initially considered that the source may emit initially A or B or C, anything. So equal probability 1 by 3. Similarly here, Pi multiplied by Hi, that is P2 multiplied by H2. P2 is what? 1 by 3. H2 we already calculated in the previous slide. Similarly for P3, H3. So this is the entropy of the source. Next, we need to find out the average information content, right? But simple. So if it generates one symbol, maybe it is generating A, or it is generating B, or it is generating C, then we write it as G1. N is 1 here because it is generating just one symbol. Then how to find out the probability here, total probability. So probability of A is equal to 1 by 2 multiplied by 1 by 3. That is if the source generates only A. So how do we get this? You see here, from state 1, it can generate A. How it can generate A? Here, this path. From state, any other state, we get A. Okay, from state 2, here, we get A. Right? From state 3, do we get A? Yes. From state 3, we can get A here. This is the path, right? So what's the probabilities here? So this sentence says if the source has to emit A, what are the different choices it has got? It may be generated from state 1, or it may be generated from state 2, or from state 3. So altogether, we need to get 1A. So we'll see here, first one. From state 1, it can generate A with probability 1 by 2. That is what mentioned here. The probability is 1 by 2, and this is the probability that the system or the source was in state 1. That is 1 by 3. That is what we considered initially, that system can be in state 1 or state 2 or state 3 with equal probability. Next, how can A be generated? Any other choice? Yes. From state 2 also, we can have a A. So that probability is 1 by 4. And this is the probability that system is in initially state 2. Thirdly, from state 3 also we can generate A here, right? So the probability is 1 by 4. So that is what mentioned here. Probability of A, and the system was initially in state 3. So these are the different possibilities of generating A. Similarly, can we generate B? Yes, from every state we can generate B. For example, from state 1 we can generate B as shown here. Or from state 2, can we generate B? Yes, here. From state 3, can we generate B? Yes, it is here, right? So it is 1 by 4, 1 by 4, and 1 by 2. 1 by 4, uh, maybe this is for B, 1 by 2, and this is for C, 1 by 4, right? For C, where is C? 1 by 4. Yes, here. Going to third state, 1 by 4. And these are the probabilities that the state is the initial state. So again, we get the answer here. Similarly, is there any chance of generating C? Then what are the different choices? I think you can do it by yourself. P, probability of C is, these are the different choices we have got. That is, uh, from state 1, it can generate C, or from state 2, it can generate C here, or from state 3, it can generate C here, right? This is what mentioned here. Okay, this is regarding generating one symbol. If it is okay, then we'll find out how to calculate the total information content. So G1 is equal to 1 by n value is 1 here, and you apply the same equation what we saw. This is the uh, probability of the first state, log of 1 by pi, the second state, and the third state, the total value. So basically we're applying the same equation Gn, what we saw in the previous slide here. Okay, now if it is a two symbol, we assume that the source will generate two symbols. Maybe it is generating A, or A and B, A and C, all the possibilities what we have. That you can refer to the tree diagram. Then how to find out these values. So suppose if it generates A, then what possibilities we have? What's the probability? You can refer to the tree diagram. I will just, for this case, I will refer to the tree diagram in the next slide. Okay, generating A. So A is here, A is here. So the probabilities are 1 by 2 and 1 by 2. Anywhere else can we do that? No, right? Okay. In the second, from the second state, can we generate A and A? A is here, A is here, and the probabilities are 1 by 4, 1 by 2. And then from the third state, can we generate A and A? A is here, A is here. So two symbols generated with the probability of 1 by 4, 1 by 2. That's what we are going to write back here. Then we have A and A. If you want to generate A and A, we can generate it from state 1 with the probability 1 by 2, 1 by 2. And this is the probability of the state being in initial state 1. And then we can also generate A and A from state 2. We can also generate A and A from state 3. Similarly, we can generate B and B from all the states. Similarly, C and B from all the states. Basically, we can generate all these size 2 symbols, what are different combinations from all the states. That's what we are going to calculate here. For example, C and B, how to generate C and B. You just refer to the tree diagram and understand how to generate CB. For example, I can just tell you how to generate CB. For example, from first state, it can generate C here, and where is B? This is here. So it is 1 by 4, 1 by 4. Next, from here, how to generate C and B. C is here, and B is here. Similarly, from the third part, C is here and B is here. So these are the probabilities 1 by 4, 1 by 4. That's what we are going to write here to generate CB 1 by 4, 1 by 4, 1 by 2, 1 by 4, and 1 by 4, 1 by 4 altogether. So many values you get. Okay. Finally, when you compute the probabilities for all the two side symbols, AA, AB, AC, as mentioned here, there are 9 values. I have not shown for all of them, but you can compute by yourself. So finally, what we compute is G2. G2, you know the equation 1 by n and the probabilities of every state. So here we have 1 by 6 log 1 by 1 by 6. That is based on this one. Here also 1 by 6, here also 1 by 6, and one more value here will be 1 by 6 if you compute. So that's why I have written here 3. 3 of the values will have the same. And here this value is 1 by 12. And 6 values here will be 1 by 12. If you compute, you'll come to know. So I have written 1 by 12 log 1 by 1 by 12. That appears 6 times. Most of them here will have 1 by 12. That's why this is the value. So altogether the value is this much. So that is G2. So okay, so this says what is the average information bits required to represent a symbol if the source emits two symbols. In the previous case, we computed G1, right? What is G1? G1 is 1.585. That means a source emits just one symbol. Then what is the average uh, size required? That is so many bits required per symbol. Suppose the source emits two symbols as shown here. If it emits two symbols, then what is the size required? It is 1.542 bits per symbol. Each bit requires so many space. Sorry, every symbol requires so much bits. So what is the general observation? General observation is the size required for G1 is much greater than G2. And G2 is greater than its overall entropy H. Okay. So as the uh, size of the messages generated by the source increases, the space required here reduces. That's why if a source emits just one symbol, then it requires more bits per symbol to store or transmit. If it generates two symbols, then it is considerably lesser than G1. If it emits three symbols, then that will be much lesser than G2. If it emits four symbols, that means A, B, C, D, A, C, B, D, A, D, B, C, and so on, like four symbols in a message, then the space required is much lesser than generating three symbols. So it becomes more and more efficient, right? Because you'll be saving more space. We don't want to transmit too much bits for every symbol. So this is one observation, and your computations when you calculate, you should follow this general observation. Okay, so that is the end of this discussion regarding the dependent source or the Markov source. So we discussed today how to calculate the entropy in case of a dependent source, and also we determined the average information content in case of a dependent source.